Hello everyone, so welcome to a CrySP series on privacy and security. Today we have Wang from MIT talking to us about using cryptography to make things slower. So he's a PhD student with Nikolai and James, I believe, right? So he typically works on system security projects. Frank is also in a unique position in a way that he's found a way of taking money from the rich and giving it to the poor. So he takes money from investors and gives it to students and researchers. So he needs some money to talk to Frank. So other than that, so Frank Wang, please help me welcome him.
Oh, I have one, yeah. Cool, thanks for having me here today. My name is Frank, and today I'm presenting Sieve. It's a system that provides cryptographically enforced access control for user data in untrusted clouds. This talk is based on an NECI paper from 2016, and so I'll kind of like go through a good portion of it, but if you want to have more details, like definitely read the paper, and I'll be around afterwards to answer other questions or go more in depth on some areas. But this kind of talk provides an overview of topics in the paper. So this is joint work with James from Harvard and Nikolai and Vinod from MIT. So just to kind of motivate the system, consider the following scenario. A user has a Fitbit that collects data on her fitness, like her heart rate, number of steps, miles run, etc. And this data is now stored on the Fitbit server, which acts as the user's storage provider. So she now wants to share different subsets of this data with various services. So for example, she might want to send only her running times for the New York Marathon to the New York Marathon service to participate in the leaderboard, or she might want to send her running times for other marathons, the Boston Marathon, for qualification purposes, and she might want to send parts of her fitness data every month to her insurance company to receive a premium discount, which is more applicable in the US, but the list can go on. So an obvious problem is that there's a major security issue with all of this. A curious storage provider who is logged in, or an external attacker like a hacker can just leak the sensitive user data from the server. So a naive approach is that users could just always encrypt their data before storing it on the storage provider. However, for example, in order to give the New York Marathon access to her data, she has to give the New York Marathon her key. And this is problematic now because the New York Marathon can access all of her data. So this approach allows users to securely store her data, but the question becomes, how does the user selectively disclose her data? Well, here's another approach, is that we can just encrypt each piece of data individually and distribute different subsets of these keys. However, the problem is Fitbit is constantly generating new data every day, and all that data also needs to be encrypted with different keys, and you can imagine now having new services, et cetera, et cetera. So now the user is just stuck with all of these keys, and the question is there a better way? And so that leads to our system, Sieve, which is a new platform that allows users to selectively and securely disclose their data. Sieve protects against server compromise. It hides key management from users. It has reasonable performance. We support revocation. We allow users to recover from device loss. And it's particularly good for web services that want to analyze user data. So just an outline for the rest of the talk. So I'll talk about Sieve, the protocol, some optimizations, revocation, how we handle device loss, and then I'll talk a little bit about the implementation and evaluation. So here I'll just present an overview of how the Sieve system looks like. So Sieve has three main principles: the user, the storage provider, which stores the user data, and web services, which are used to analyze the user data. And so there are three main components in Sieve: the Sieve user client, the Sieve storage daemon, and the Sieve data import module. So first, the user, using the Sieve user client, tags and encrypts her data with attributes that represents access for future web services. For example, location equals US, year equals 2012, and type equals fitness, and sends this data to the storage provider. This data can either be generated by the user directly or by a device like a wearable and uploaded to the storage provider. So when the user first visits a web service, she generates a decryption key that corresponds to a policy on the types of the data the service can access. For example, year is less than 2013 and type equals fitness, and gives this key to the web service. So later in this talk, we'll also show how we can revoke a web service's access after you granted it. So now the web service has the ability to download and decrypt user data. So the user sends a user data request to download the encrypted data. And since the web service has a decryption key and the data, it can now decrypt the data using the Sieve data import module. The web service now stores the data in its own servers in storage, and it can do its own analysis on it. One thing to note about all this is that all these interactions can be asynchronous. So in fact, the user doesn't even need to be online after she gives the web service the key for it to access the data. So now I've given you an overview of Sieve. We can talk a little bit more specifically about the security problems and threat model. So we assume the storage provider is a passive adversary. This means that the adversary can read all the data, but we assume that it follows the protocol. Web services are trusted with user data once they are given access to it, and we assume the user and her devices are trusted. So in order to securely and selectively disclose data, we use attribute-based encryption, ABE. We also assume a user private public key that is generated at the start of the ABE system, just like any other public key crypto system. And so just to present an overview of ABE, there are three main functions. There's the generate decryption key function, encrypt, and decrypt. And so first, generate decryption key takes in a policy and an ABE private key and outputs an ABE decryption key. So a policy is just a predicate connected by ands and ors. For example, year is less than 2013 and type equals fitness. And then second is the encrypt function, which takes in attributes, the clear text data, and ABE public key, and outputs a ciphertext. So example of attributes are key value pairs, such as location equals US, year equals 2012, and type equals fitness. So finally, there is a decrypt function that takes in a ciphertext and a policy, and it only decrypts the ciphertext if the ciphertext attributes satisfy the key policy. One important thing to note in ABE is that these attributes and policies are all in clear text. So you kind of know where I'm going with this. So as you may have noticed, ABE fits very well into the Sieve architecture. So let's take a look at Sieve with ABE included. So first, the user uses the ABE encrypt function to tag and encrypt her data, and she sends this data to the storage provider. So when she visits a web service, she generates an ABE decryption key, and she gives that to the web service. Finally, the web service can then download the encrypted data and use its key to perform ABE decryption to get the clear text data. So the question is, are we done yet? Well, not quite. So there are still a couple of challenges with ABE. So since ABE is a public key crypto system, it's much slower than symmetric key cryptography. So here in our paper, we describe two optimizations. First, we use hybrid encryption, and second, we use storage-based data structures. So how many people are actually familiar with hybrid encryption? Okay, that's like half. Okay. All right, so I'll just go through it quickly because it'll be useful when I talk about storage-based data structures. So in hybrid encryption, first you generate the symmetric key, and that key is used to encrypt the data. Then the ABE public key is used to encrypt the symmetric key and a GUID, which just represents the location of the actual encrypted data block in the storage provider. And this way, symmetric key encryption, the faster encryption method, can be applied to the larger data, and ABE is applied to smaller and fixed data sizes. So both these encrypted objects are now uploaded to the cloud, and for the rest of the talk, the block that is encrypted with the ABE key, we'll call it the metadata block. And in the storage provider, the data block is indexed by the GUID, and then the metadata block is indexed by the AB attributes. And so for future updates that require uploads by the user or downloads by the web service, the user and web service can just cache the symmetric key and GUID, and they can just use the GUID to access the data directly to perform symmetric key operations. Cool. So now I'll talk a little bit about this kind of extension of hybrid encryption, which we call storage-based data structures. Our goal is to really place more data under one metadata block. So we do more symmetric encryption and can store more data for one single metadata block that's AB encrypted. So in this case, let's say we have a bunch of data blocks that fall under the same tags. So for example, a user might want to store a month's worth of data under the same tags. First, the user generates a symmetric key, like in hybrid encryption, and encrypts her data. Then she creates an indirect GUID table and encrypts the GUIDs with the same symmetric key. We will call this the indirect GUID table. And the user finally encrypts the symmetric key with her public key using the appropriate attributes that fit, have all that data fit under it. Yes?
So they're all the same symmetric keys?
The question was, are those all the same symmetric keys? Yes. So she can cache, now she can cache the GUID table and metadata block with the AB key to retrieve updates to this data in the future without having to do the AB operations. So now I've kind of told you a little bit about the performance hacks we made. The next issue I'm going to talk about is revocation. And so let's go back to our initial Fitbit example. So suppose a user wants to switch insurance companies. So she wants to revoke the insurance company's access. However, what if the old insurance company becomes compromised in the future? So remember, the old insurance company has cached keys that it can use to access the user's data. Well, that's problematic. So we need a way to encrypt the data to provide cryptographically strong revocation. And so, however, remember that our data was encrypted using hybrid encryption and storage-based data structures. So what we really need to do is to re-encrypt the metadata and data blocks. And so it's easy to re-encrypt the AB encrypted metadata block. It's much smaller than the size of overall data. You can just download it, re-encrypt it, and upload it again. But these data objects can be pretty large. So how do we re-encrypt the data object? Well, we can always just download it, re-encrypt it, and upload the data object. But that requires a substantial amount of bandwidth and client-side computation. The question is, can we do better? And so our solution is we use key homomorphism. So this allows us to change the key in encrypted data. And so using this technique, we can have a symmetric cipher that provides in-place re-encryption. And so the guarantees we get out of this is that the provider does not learn the old key, the new key, or the plaintext. More specifics on the scheme are in the paper. And so here I'll describe how the full revocation process works. So let's say we have a simple Sieve data object. We have a metadata block with a symmetric key and an encrypted data block using that symmetric key. So one important detail to note here is that if the user wants to have revocation, she has to introduce an epoch number as an attribute when she generates and tags data. And similarly, she has to include this epoch as part of a policy for a web service key. And so this number just represents the number of revocations that have happened. And the purpose of this epoch number is that during revocation, it allows users to re-encrypt just the data with attributes affected by the web service's key policy that's been revoked, rather than re-encrypt all of their data. And so then the user generates a rekeying token, which is a function of the old key and the new key. And she sends this token to the storage provider, who applies it to the appropriate data block and then deletes this token. And this causes that data block to be rekeyed. And so next, the user generates a metadata block, a new metadata block based on the new symmetric key. and encrypted using an ABE public key with the same attributes, but now with an incremented epoch number. And this now replaces the old metadata block. So the user does this for all the data blocks that the revoked web service had access to. And finally, the user issues new keys to web services whose data has been changed or affected by the revocation. So the final challenge that we solve is this idea of device loss. So the question is now, what if a user loses her device? Because the user now has this ABE private key. And so if the device is lost, the loss of the key requires kind of resetting the whole system, which means re-encrypting all her data and issuing new keys, because you need to now generate new ABE public key, private key pair, and now re-encrypt all the data. So is there a way for a user to recover from device loss? And our solution is just to use secret sharing. So a user just splits her ABE private key across devices, and secret sharing requires a threshold to reconstruct the secret. And so you reconstruct before using the ABE private key. And so when device is lost, you just gather your devices to reconstruct the secret and just issue new shares. So now I'll talk about our implementation and evaluation. So the Sieve implementation, in terms of cryptography, we use the libfank library with Stanford PBC for ABE. And we implement it with both AES, which doesn't require revocation, and randomized counter mode with ED448, which does provide us with revocation. And so for the 3 different components I described earlier, it required about 1,400 lines of code to make the Sieve user client. And it required about 1,000 lines of code for the Sieve storage daemon. And we used MongoDB and BerkeleyDB in the background. And the amount of code that's required for the Sieve data import module, that's service specific, which kind of goes into our evaluation, which we try to answer 2 main questions. Is it easy to integrate Sieve into existing web services? And 2, can web services achieve reasonable performance while using Sieve? So our evaluation setup is we use a multi-core machine with 2.4 gigahertz of Intel Xeon processor. Web service run on a machine's loopback, so we minimize network latency, and we focus on cryptographic overheads. And so for Sieve, we integrated with 2 open source web services, OpenMHealth, which represents small data. And what OpenMHealth does, it helps users visualize their health data. And so just to give a sense of size, 1 week's worth of health data is about 6 kilobytes. And we integrated with Piwigo, which is a photo sharing app, and it allows you to edit and display photos. And a photo is about 375 kilobytes. And we show it's relatively easy to integrate with Sieve. So the lines of code required for integration were about 200 lines for OpenMHealth and about 250 lines for Piwigo. And this is just a small fraction of the total number of lines of code in the web service itself, and shows that Sieve is easy to integrate with. And so here are kind of just some results for OpenMHealth and Piwigo using the ED448 library with key caching. So we have acceptable performance for both case studies. We see that reading and writing a week's worth of OpenMHealth data takes less than 1 second. And the time for the read and write time for Piwigo is a little bit longer because the data is larger. So there's a performance gap between using AES and ED448. The performance gap for reading and writing widens for larger data like photo data and Piwigo. And the reason for this is that ED448 is not hardware optimized like AES, but we expect that this performance to be improved in the future with more research and better hardware support.
So,
yes.
So reading here is for the service and writing for the client?
Yeah, the client writes and a service reads, yeah. So we also show that we have pretty good per core throughput. And so OpenMHealth storage writes, we can do 50 megabytes per second, and we can import about 70 users per minute on 1 core using ED448. And for Piwigo storage writes, we can do about, the throughput is 200 megabytes per second. And for web service imports, we can do about 14 photos per minute. So we also show that revocation performance is reasonable. So to re-encrypt a metadata block with 10 attributes takes about 0.63 seconds. To rekey a 100 kilobyte data block takes 0.66 seconds. And to generate a new 10 attribute key takes 0.46 seconds. And secret sharing is fast. For 5 shares and a threshold of 2 to reconstruct, splitting the key takes 0.04 milliseconds, and reconstructing the key requires 0.09 seconds. So to kind of summarize the results, it required less than 250 lines of code to integrate with our case studies. We can read and write data in a reasonable amount of time. We have good per core server throughput for storage writes and application data imports. And revocation functions take less than a second, and secret sharing takes a negligible amount of time. And so Sieve is related to prior work in several areas. There's much work on cryptography to protect untrusted servers, such as shadow crypt, Sunder, et cetera, but they don't really solve the same problem Sieve solves. Sieve provides easy key management for users that want to securely and selectively disclose their data to various web services. And in terms of ABE storage and predicate encrypted storage, Sieve is the first ABE system to provide a complete revocation scheme and allow users to recover from device loss. Other ABE systems have either incomplete revocation schemes because they only re-encrypt the metadata block, and they're not able to recover from device loss. And finally, Sieve also provides cryptographic guarantees to compare to access delegation schemes like OAuth, and it's more expressive than AAuth. So kind of to conclude, today I presented Sieve, which is a new access control system that allows users to selectively and securely expose their private cloud data to web services. We efficiently use ABE to manage keys and policies. And there's a complete revocation scheme that's compatible with hybrid encryption using key homomorphism. And it is easy to integrate and has reasonable performance. So I'm open to any questions. Okay. Microphone is closer, so we'll go there.
Thanks for your talk. So I have 2 questions. One, can you say more about the symmetric re-encryption scheme?
Yes, so it's just a standard, it's a standard just like key homomorphic scheme. So it uses, it's based on random oracles. What specifically do you want to know about it?
Right, tell me the construction.
Oh, okay. Okay, I wish I had a board, but it's, oh, great. But no marker. I can show, there's no marker, but it's just like, it's a pretty standard one. It's like, you hash a value x and then you raise it to the key. And so then when you multiply it, the keys add in the top.
So there's a bit of a public key operation.
There's a bit of a, it requires Diffie-Hellman. So
okay.
Yeah, if that's, there's a public key operation. Yeah.
So it's not strictly symmetric, that's what's surprising. Okay.
So yeah, I mean symmetric in the fact that there's only one, there's no public-private key. Right. But there's a Diffie-Hellman operation. So it's not like based on AES or anything. So you do need mathematical assumption.
Right. And the other question was, in your threat model, you said that the storage server was passive.
Right.
So what goes wrong if they're an active adversary?
So what goes wrong is, so it's passive. The reason it's passive is mainly for revocation. So if the storage provider does not delete the keys or the old data, then kind of revocation becomes pointless because they can just leak this data to the old, to kind of people who have the old cache keys. And so kind of like revocation becomes pointless if you have an active adversary. And so yeah, the storage part can actually require active adversary because nothing is really happening. They're just storing encrypted data and kind of like reading and writing. But the revocation requires a passive adversary.
Great.
Do you want to? We can do the mic, or I can repeat the question.
I use the mic, it'll get recorded.
Oh, no, I would repeat the question, but that would be my interpretation of your question. So.
Question on implementation. Have you approached any vendors about applying this to their products?
Yeah, so actually we've been approached by a couple of people. I haven't had time to follow up with them. I think they're, so people are extremely excited from the revocation side because people want to be able to re-encrypt their data kind of server side without their clients having to do anything. So like potential vendors who are excited about this are people who have large cloud storage services like Google or Microsoft. Amazon may or may not care, or they might secretly care. But we've been approached by kind of Google and Microsoft to kind of talk about this. And I think just from just this storage perspective, I think a lot of a lot of the people who are very interested in this idea of like a decentralized web have kind of come and talked to us to consider integrating ABE in. But I think the hard part about doing that is that the ABE library is actually pretty slow because we use this PBC library instead. But there are new libraries that give us promise that like ABE will actually become faster.
The other thing is that on some of these devices, I've never used a Fitbit, for example. Does it require something in the Fitbit firmware to enable the encryption before it gets sent out from the device?
Yeah, so the Fitbit models, so the encryption isn't done on the Fitbit. So usually what happens in Fitbit is that you have it's Bluetooth connected. And so like the data would be transferred to your computer before being uploaded.
So it gets staged before it gets...
Yeah, or like staged to your mobile phone before it's uploaded. So that's kind of, we don't imagine changing that flow. Like Fitbit would never directly connect to a Wi-Fi device. They would just Bluetooth anymore. If it's a Wi-Fi device, then yeah, you do need separate hardware.
So that really helps with the implementation of this because the devices themselves need the modification.
Yeah.
Good. Thank you.
Yeah.
So your attributes in the ABE are like a traditional form of metadata. Right? They reveal things about you. So like in the example you showed, where you had attributes that were like date and location, that means you have a clear text location history.
Right, yes.
So do you have any thoughts on what to do with that?
Yeah, so I mean, I think there's kind of two separate responses. So one is it kind of depends on what data you're looking at. I think for these kind of fitness-related situations or these kind of user data generated by like these IoT-like devices, usually the data itself is way more sensitive than the metadata. On the other side is you can also use this idea of predicate encryption, but it's just much slower. So you kind of have this trade-off between privacy and speed, which is a very common trade-off. So if you really cared about kind of keeping your metadata private, you would have to use predicate encryption, which is not much slower than attribute-based encryption, and kind of like depends on your model, kind of like what you want to reveal in the metadata or not.
Thank you. Yeah, I really found your talk very interesting. I actually worked in a similar problem of actually security sharing data within the cloud, in particular for multi-nation users. And actually, one of my solutions I did end up using self-text policy attribute-based encryption, but I ended up combining it to have efficient revocation with proxy-based encryption.
Yeah.
Nonlinear pairing-based, right? And in my case, I was actually like encrypting the entire data content that was stored within the cloud. I guess in your case, it's different, right? Because you're actually just encrypting the metadata block.
No, so I'm encrypting both blocks. So I do use some form of proxy re-encryption. I use kind of the techniques borrowed from proxy re-encryption.
Right.
Except, yeah, I mean, it's the techniques from proxy re-encryption. It's just used with a different application. So a lot of the techniques have remnants of proxy re-encryption.
Okay, yeah. Okay, so it'd be interesting to compare the performance, I guess. Also, a quick question is with respect to where the keys are actually stored, right? Microsoft is considering an Untrusted cloud provider. Is that similar to your situation where like the private key material is maintained with the mobile device owners themselves?
Yeah, so the private key would be on like a user's mobile device or a user's computer, or it kind of be split across that.
Right. Okay.
Yeah. So the user would keep the key in some secure location, kind of like you can imagine like an SSH private key, like they can password protect it, et cetera, et cetera.
Sure. Okay. Sounds good. Thanks.
right, so you said you secret share the key across several devices. In our own group, we have Aaron, who's worked on something called Shatter, which does something similar, only it looks like you said that you actually reconstruct the key, whereas in Aaron's system, the key is never reconstructed, and the actual private key operation is done in a distributed manner. So is it correct that you actually reconstruct the key in a central place, and what could you do to avoid that?
Yeah, so we do reconstruct the key in a central place. What can I do? We would have to have kind of an encryption scheme, as you described, that allows you to, again, kind of like a distributed ABE. So you'd be able to if you have multiple keys, like half keys, like someone could decrypt half of this, decrypt half of that, and eventually by the time it makes it to the web service, it would be fully decrypted. I'm not too familiar if there's anything related to this idea of like distributed ABE decryption or encryption, and
the user uses their private key just for decryption key generation.
Right.
So it's that operation that needs to be split.
Yeah, so that operation needs to be split somehow. I haven't heard of kind of like anything so far that kind of does that, but I think that would be an interesting question for sure. I don't know kind of like if there are any similar things for like IBE or something like a little bit less general than ABE, but yeah, that I would need that for sure in order to kind of like issue these decryption keys.
Well, IBE you can definitely do with IBE. It's pretty straightforward to do that.
Okay.
So maybe it will work with ABE.
Yeah.
Just a quick observation, I think, not a question, but in your adversarial model, you talked about different things that you were concerned about. I didn't see anywhere in there where you took web services colluding with each other into account.
Sorry?
So the different web services colluding with each other to decrypt your data, for example, right?
Oh, okay.
So just a comment there that maybe perhaps you should consider that.
Okay, yeah, so the observation was about I didn't consider web services colluding each other, and so, yeah, they are allowed actually to collude with each other, and they won't get more information than they would have gotten otherwise, and that's kind of a guarantee out of ABE. So if like web services collude, they won't learn any more information than they would have gotten like individually, and they would like put their information somewhere, like that bucket won't be bigger if they all colluded.